So at this point, we have seen some examples of what partition functions look like. But the question that really we should be thinking about is, how do we get to these partition functions? I've introduced a couple for like a monatomic ideal gas. We can look at some other ones, but how do we get to these partition functions? And if you remember, we need to know the energies, right? These EJ values, because they go into the sum that makes up a partition function. And these energies are the energies of a system, meaning a bunch of molecules, like 1 mole or something like that. And in theory, we find these by solving the Schrodinger equation for our specific system with its given quantum states and whatever. But in practice, this is essentially impossible. We can solve the Schrodinger, or we can approximate the Schrodinger equation solution for like 1 molecule at a time, or even maybe a few molecules at a time. But thinking about a whole mole of molecules, there's basically no way, with current methods at least, and no way probably ever, but never say never, that we can find the possible energy values for an entire mole of molecules at one time. Something like, or like even a liter of gas, it's even less than a mole. So what we want to do instead is break down this system into individual components, or individual molecules or atoms, and see if we can take the information and this is the whole point of statistical mechanics, is we want to take the information about a single molecule, the energy levels and what we know about it, and work up to a bulk system, right, to having n particles or whatever. So in our discussion, we are going to consider only independent molecules where they don't interact with each other. That simplifies things. So basically, for all this introduction to statistical mechanics, we're only going to consider ideal gases, and the simplest thing we can do is say, okay, well, let's take our energy for a particular state. If we have a bunch of molecules, well, n molecules given volume, is we take each particle, the energy of a particle, we'll call the particle A, which particle we're considering, and what's its energy state. So there are a bunch of different possible energy states it could have. So maybe if we're thinking about electron orbitals, maybe one particle is in an s orbital, one's in a p orbital, and they have different energies. And then we add up all the different particles we have, right? So each particle will have its own energy state, and we have a bunch of them all the way up to n. So in theory, we could set up a sum that looks like this. So then we can go ahead and write out the partition function for this whole system. We'll call this state L, just not to keep it, right? We have I, J, and K already, right? So this, for a particular state L where we have specific values of our energy states for our individual particles, for all the different possible values of L, we can have all the different combinations of energy states and particles. We then add up e to the minus beta EL, which is, we can then decompose this into adding up over all of our different energy levels, the possibilities, e to the minus beta, and we have this sum here, right? EIA plus EJB plus EKC plus ... Okay, and that would be, in theory, how we could do this. Now, there's one problem with just adding it up like this. Oh, one further step we can take that simplifies this is we can separate this out, right? We have these different I, J, K sums, but the way our partition function is set up with the exponential, we can actually break these up, right? We are adding these together. That means we can separate out these into individual exponentials. And this breaks up into Q is equal to, sorry, this is a really important part and almost skipped over it, e to the minus beta EIA times e to the minus beta and summing over. So we for particle A, we sum over all of its energy states. For particle B, we sum over all of its energy states. For particle B. For particle C, we do the same thing. And we can keep doing that, but the nice thing is if all these particles are the same, we just get copies of the same partition function. Partition function for particle A, B, C, they're just going to keep multiplying, and that will just lead us to Q raised to the n. We'll just have n copies of our individual molecule partition function. Right, so the little q here equals a single molecule partition function. Whereas big Q represents the total system partition function, meaning however many molecules we have, it takes all of them into account. Okay, and you might think, okay, we're done. This looks great. We have a way to express if we can find these values of little q, then we just raise it to the n, and we have big Q. There's one last thing we have to take into account. This assumes that we can tell all the particles apart from each other, and we can label them. Right, that's the key, is that we can write these labels for particle A, particle B, particle C. For most cases with quantum mechanics, our particles are not distinguishable like this. This is a general principle of quantum mechanics. Usually, and for an ideal gas certainly, particles are indistinguishable, meaning we can't label them, we can't tell them apart from each other. In practical terms, what this means for our big Q is that if we just do Q, little q raised to the n, we will overcount the number of possible ways that we can do this. Because there are lots of different ways we can get the same total energy. Just a brief example to sort of illustrate why we need to take the next step we do. Let's imagine we have in one particle in energy state 2 and a bunch of other ones all in energy state 7. Just to pick a random number here. These all add up to the same total energy, but this 2 could be for the first particle, it could be in the second particle. All these would give the same answer even if we switch these to different spots. But we can't tell these apart from each other quantum mechanically. They're indistinguishable from each other. So if we count each of those possibilities, we're overcounting. There's too many copies of Q that we're multiplying together. We should really only include one of these arrangements instead of all, in this case, 4 different possibilities. And mathematically, the way that we do this is we divide by n factorial, the total number of particles factorial. That corrects for the overcounting that we'd have by assuming our particles are distinguishable when they're actually indistinguishable. Long story short, big Q is equal to little q raised to the n divided by n factorial, and that n factorial deals with this issue of indistinguishability. And so if we can find our individual partition functions for individual molecules, we can then find the system partition function and use all these functions that we have described. Find average energies, find average pressures, et cetera, find probabilities of specific energy levels and things like that. So that is that's our next goal, is to for chapter 18 is how to find Q. And again, we're gonna stick to simple examples of an ideal gas in either monatomic or diatomic. We won't get any larger than diatomics, mostly because the rotation and vibration partition functions get much more complicated. But yeah, that's where we're going with this, and that concludes this video.